Speaker 00. This question comes from the 50th IMO competition, the International Mathematical Olympiad held in Germany during Wei Shen's second year of high school. That year, Wei Shen achieved a perfect score, marking his second consecutive perfect score in the competition. So, let's delve into one of the geometry problems presented. We're given an isosceles triangle ABC, where the length of side AB is equal to the length of side AC. The angle bisectors of angle CAB and angle ABC intersect sides BC and AC at points D and E, respectively. Point K is defined as the incenter of triangle ADC. We're told that angle BK, specifically this angle here, measures 45 degrees. The task is to find all possible values for angle BAK. As you can see, there's a substantial amount of information packed into this problem. If a problem of this nature were to appear on the Gaokao, China's national college entrance examination, it would undoubtedly be more challenging than even the most difficult problems we've seen in recent years. So, let's explore how we can approach and solve this problem effectively. As always, we need to begin by focusing on the goal. The primary objective of this problem is to determine angle BAK, or rather to identify all possible values that angle BAK can take. Considering that BAK is an angle within a triangle, we can connect it to our existing knowledge of triangles. Under what specific circumstances are we able to definitively determine the measure of an angle? We can think of finding the trigonometric function of this angle, and then determining the value of the angle through the trigonometric function value. This angle is an interior angle of a triangle. Combining the trigonometric function values of special angles in a triangle, we can find the value of this angle. So, this is the problem-solving approach we can think of right now. Since we need to find the trigonometric function value of this angle, we'll express the degree measure of that angle. Here, based on the meaning of the problem, we've drawn a simplified diagram. Let's see how some of the extra information here comes about. Isosceles triangle ABC, which means AB and AC are equal. AD is the angle bisector of angle BAK, and BE is the angle bisector of angle ABC. AD and BE intersect at a point which we label as F. Point K is the center of the incircle of triangle ADC. Based on the information given in the problem, that is, the conditions we're given, let's look at condition 1. Triangle ABC is an isosceles triangle. So, the angle bisector AD is definitely the perpendicular bisector of the base. In an isosceles triangle, it's both the angle bisector and the perpendicular bisector of the base. Therefore, it's easy to see that this angle is 90 degrees, so angle ADC equals 90 degrees. This is derived from the information given in the problem. Since BE and AD are both angle bisectors within this triangle, their intersection point should meet certain conditions. What we can deduce is that point F should be the incenter of triangle ABC. Since it's the incenter of triangle ABC, if we connect CF, then CF is obviously the angle bisector of angle ACD. The three angle bisectors of a triangle intersect at one point, so CF is the angle bisector of angle ACB. Keep up, everyone, because there's a lot of information. Since CF is the angle bisector of angle ACB, then CF clearly passes through point K, because point K is the center of the incircle of triangle ADC, so it will definitely pass through the angle bisector of angle ACD. Therefore, line CF passes through point K. These are the basic pieces of information we've extracted from the problem. Now let's look at the third piece of information. If we want to find the value of the target angle, we first need to assign it a value. Let's set the measure of angle BAK to 4x degrees. I'm foreshadowing this for a reason. Why 4x? Many of you know that for an isosceles triangle like this, we usually wouldn't set it as x. Commonly, we'd set it as 2x, so that after bisecting, the angle becomes x. So, why are we setting it as 4x here? It's for the convenience of representing other angles like 1CF and 1BC. You'll understand why we set it as 4x when we look further down. If angle BAK is 4x, then let's see what angle DAK is. This angle is 2x degrees. This angle is 2x degrees. Let's see what angle ACD is. ACD is 90 degrees minus 2x. So, by setting angle BAK, we can express the measures of many of the angles. We can deduce that angle ECF equals angle D, which equals half of 90 degrees minus 2x. Its bisector, that's 45 degrees minus x.
Angle ECF is 45 degrees minus x. Let's see if angle EBC is also 45 degrees minus x. Isn't this angle also 45 degrees minus x? Because angle ABC and angle ACB are equal. This is the angle bisector, so we see this angle is 45 degrees minus x, and this is also 45 degrees minus x. At the same time, we also deduce the angle
EBC is equal to 45 degrees minus x. Now, let's explore what other angles we can express using these given conditions. Let's take a look at angle BAK. What should its measure be? If we consider triangle ABE, we can see that angle BAK is an exterior angle of this triangle. In other words, this angle is an exterior angle of the triangle. And remember, an exterior angle is equal to the sum of the two non-adjacent interior angles. In this case, that's 4x plus 45 degrees minus x. So, BC is equal to 45 degrees plus 3x. Now that we've expressed BC in terms of x, let's use the information the problem gives us. The problem states that BC is a 45-degree angle. Given that, what is the measure of angle KC? KC is simply this angle, BAK, minus 45 degrees, which means it equals 3x. This is derived directly from condition 2. Using this condition, let's see what other angles we can deduce. Now, let's move on to condition 3. This angle is 45 degrees minus x. Also, remember that this angle is 90 degrees in right triangle BFD. With this information, can we calculate angle BFD? Yes, we can. BFD is 45 degrees plus x. And since BFD and angle CFD are equal, we can also deduce that angle CFD equals angle BFD, which equals 45 degrees plus x. So we've successfully found another angle in terms of x. Once we've expressed these two angles, can't we also express the other angle, EFC? Angle EFC would be 180 degrees minus these two angles. Since these two angles add up to 90 degrees plus 2x, then 180 degrees minus that is 90 degrees minus 2x. So, we've expressed all these basic angles. Like this angle here, 45 degrees, this one is 3x. I'll write this angle over here, it's easier to see. So that's 90 degrees minus 2x. Now, to find our target value, we really just need to figure out what x is, since we set back to 4x. Okay, so now let's take a moment to see what we've learned in the past that can help us relate the angle measures to the sides of these triangles. Think back. In a triangle, haven't we learned about the law of sines? It's a pretty useful tool for this kind of problem. So, with that in mind, let's focus our attention on triangles EFK and IKC. Looking at these two triangles, we're going to use the law of sines to help us find the relationships between their sides and angles. The law of sines, after all, is specifically designed to connect the sides of a triangle to the sides of their opposite angles. It's the perfect tool for this job. Looking at triangle EFK, we can see that side FK corresponds to the 45-degree angle. So FK over sin 45 degrees is equal to IK over angle EFK. Now, remember that angle EFK is the same as angle EFC, which we already figured out earlier. So that means it's equal to IK over sin 90 degrees minus 2x. From here, we can express FK in terms of IK and the angles. FK is equal to IK times sin 45 degrees all over sin 90 degrees minus 2x. Great, now we have an expression for FK that we can use. Now, let's shift our focus to triangle EKC. In this triangle, KC corresponds to the 3x angle, so that equals sin 3x degrees. Also, it's important to notice that these two triangles share a common side, which is EK. That also equals 1k over tangent angle ECK, which we can express as tangent 45 degrees minus x. Through this comparison, we arrive at the equation where KC equals 1k times tangent 3x, all divided by tangent 45 degrees minus x. Now, combining these two equations, isn't it clear that we can derive the ratio of Fk over Kc? Since 1k is a common side in both expressions, we can directly cancel it out, simplifying our equation. This then equals tangent 45 degrees multiplied by tangent 45 minus x over tangent 3x multiplied by tangent 90 degrees minus 2x. Through this, we then arrive at the ratio of Fk to Kc, effectively obtaining an equation that relates these segments. Now let's take a step back and see which condition we haven't fully utilized yet in our calculations. Ah yes,
K is defined as the incenter of triangle ADC. Given that it's the incenter, connecting DK creates the angle bisector of angle ADC. Then, based on the angle bisector theorem, a concept we all learned back in middle school.
So can we then derive the ratio of Fk to Kc? Fk over Kc equals Fd over dc. And the ratio of Fd to dc can be expressed using the law of sines in triangle FDC, using the sine values of the angles. So it also equals sin 45 degrees x over sin 45 degrees plus x. Now let's label these two equations as equation 1 and equation 2. Actually, Fk over Kc means these two equations are equal. Since these two equations are equal, we notice a sin 45 degrees x term. We've set angle BAK as 4x, so x is obviously less than 45 degrees and greater than 0, as it's an interior angle of a triangle and thus less than 180 degrees. Therefore, sin 45 degrees x is clearly not equal to 0. From equations 1 and 2, we can eliminate the factor sin 45 degrees x. So from equations 1 and 2, with these two equations being equal, we arrive at this equation. Sin 45 degrees multiplied by sin 45 degrees plus x equals sin 3x multiplied by sin 90 degrees 2x. We've obtained this equation. Now, how do we solve for x on both sides of this equation? We simultaneously apply the trigonometric product to sum formula to both sides. This yields cos x minus cos 90 degrees x equals cos 5x 90 degrees minus cos 90 degrees x. On both sides of this equation, cos 90 degrees x and cos 90 degrees x cancel out directly. We are left with cos x equals cos 5x 90 degrees. Okay, so combining what we said earlier, since x is greater than 0 and less than 45 degrees, these two cosine values are equal in only two scenarios. First, the two angles are equal. X equals 5x minus 90 degrees. Second, x equals the negative of 5x minus 90 degrees, which means 90 degrees minus 5x. This equation deduces the relationship between these angles. It's easy to solve. X equals 22.5 degrees or x equals 15 degrees. We've found the value of x. So, what are the possible values for angle BAK? We set angle BAK as 4x, so its values could be two possibilities, 60 degrees or 90 degrees. These are all the possible angle values for angle BAK. So we've solved the problem. Let's review. The problem gave a lot of information, and it tested many knowledge points like the exterior angle of a triangle, the angle bisector of a triangle, the incenter of a triangle, including the law of sines. After that, we can use sum to product or product to sum formulas. At this step, we can also use product to sum. If we don't analyze the angle's degree, we can directly use product to sum to transform it into the product of two sine values equaling 0. They each equal 0. Finally, we find its degree. So, this problem has a lot of information. This was a very simple problem in that year's competition. The 50th Mathematical Olympiad was also the year Weishan became a legend because a very famous problem came out that year which tested the Mandelbrot set. It was also the final problem of that year's competition. In fact, only Weishan solved that problem in the Chinese competition. Weishan also became a legend because of that problem. Okay, I'll share this problem with you all. If you guys have better solutions, please leave them in the comments section and we can discuss them together.